right. So circuit breakers, if it's less than 20 amps, it shouldn't trip. If it's more than 20 amps, it should. Historically, there have been some breaker manufacturers that would make a breaker that they don't trip. You could put 40 amps on a 20 amp breaker and it just gets warm, like you can test with your infrared tester.
So what is protection there then, if they don't trip and put in?
No protection. The wire melts. Maybe the wire becomes the fuse.
So
If your circuit breaker doesn't work, you have no overcurrent protection, other than maybe the circuit breaker in front of that one. Yeah.
So if you put a 20 breaker on a circuit has like a wire circuit wired for 30 amp, that breaker would it wouldn't work right. It would just.
If you put a 20 amp circuit breaker that has on a circuit that has what, 30 amp wire?
Yeah.
Oh, okay. So if I had a 30 amp load and I didn't have a 30 amp circuit breaker or something that would accommodate this load, and I said, well, I have a 20 amp, I'll just replace it with a 20. It's going to trip all the time.
Oh.
Yeah. In fact, for a continuous load, whatever your load is, let's say your lighting circuit is 30 amps. For a continuous load, because we have a continuous load is a load that operates for more than 3 hours at a time. So we have our lights on all day. In fact, we have this TV on all day, right? But we have our lights on all day, and we're gonna, that's considered a continuous load. So we're gonna multiply the 30 amps by 125%. So we're gonna take 125%, which is
7.5 times plus.
so 37.5. So do we have a 37.5 amp breaker? So we go to the next standard size. Next standard size would be a 40 amp breaker. So a 40 amp breaker is what we put on 30 amps of lighting load.
Is there any way easy way to test the breaker to see if it's functioning properly or when it breaks down? Or?
If you suspect that your breaker is tripping because you have a weak breaker, you can replace the breaker with the one that you had just purchased or one that you know that's working, and take your breaker and get it tested. But if your new breaker that you replaced it with does not trip, I would just throw the other one away. Because I mean, a 40 amp breaker, depending on the panel type, this could cost you $12 to a couple $100. So depending on what type of breaker you have, you might just throw it in the garbage because it's not worth driving to a place to get it tested.
If you want to test it, make sure that they do trip.
I've never heard of anybody in a facility doing that. That's possible. If you have a load that you could place on a circuit and then you're locking it with your amps to see that it trips when you exceed 30 amps on it, you could physically do that. I don't know if there's a need to do that though. I don't think there's any maintenance requirement in the industry or at Caltrans that would say that should be done. Make sure they actually function. There is, like I said, about actually turn them off and turn them back on again. But as far as making sure that they trip, no, I've never heard of a requirement that does that. Good question.
Just a quick one. The breaker and the load, the wire has to match that circuit too, right? Or it could be a weak point.
Yes, exactly. So I have 30 amp wire. I can get number 10 American wire gauge wire, which is maybe about the size of a pencil lead on these colored pencils, but about that thick, not the tip, but the actual back, if you look at the back. So I can get a copper wire that size that will handle 30 amps, but because I'm not going to continuous load and my overcurrent protection is 40 amps, I need to have 40 amp wire. So would I have to go up to the number 8 American wire gauge conductor? So yes, our circuit breaker protects our wire, and our wire handles the load. So whatever your load is, your wire needs, and whatever circuit breaker, it all has to be cohesive, I guess is the word. So we have a 40 amp circuit breaker. It should be tripping. Now they trip two different ways. They trip because of an inrush current, what will pull the breaker closed, and then they also trip through heat. So once, if we have 80, let's see, if we have a 40 amp breaker, and we put 160 amps on it, it's going to trip relatively fast. And it's going to trip from the other method through that inrush current. It's going to pull that circuit breaker closed. The other way it might trip would be if it was 41 amps. If I put 41 amps on there, now it's going to be kind of like a thermostat in your room where it has a bimetal strip and one side will get warmer than the other and it'll just open and it'll break the connection. So that's a circuit breaker and how they trip. Circuit breakers have an AIC rating. So this is a 40 amp circuit breaker. Let's say I take my wire strippers and I cut the live conductor with another live conductor. So I have two different live conductors. This is on a different circuit breaker than this one. I cut them at exactly the same time. They're on different phases. What's going to happen? I cut these both at the same time with a same tool. You've never done that, huh?
You weld your,
I've done that. Well, quite possibly in a way you're going to weld it. I'm going to cut this. Hopefully my breaker's going to trip, but I'm going to create a small arc blast. It's going to destroy my tool. I'm going to weld or probably some slag on here. I'm going to burn a hole in this. The hole is probably going to be, again, about the size of 10 gauge wire, about the size of that lead on the end of a colored pencil. And how many amps do you think it takes to burn a hole through steel that big on this much surface area?
Very high amperes.
Probably pretty high. How much do you think? Would it be 40 amps?
Depends on your tool.
It tripped the circuit breaker, but it burned my tool.
That is short circuit.
So more than 40. Definitely more than 40.
More than 40.
It depends on the distance of the tool, I think.
It depends on a lot of factors. Generally, when you blow a hole at the size on the surface area that I talked about, this is going to be about 4,000 to 6,000 amps.
Well,
Wow.
So about 4,000 to 6,000 amps would do that. So how are we putting 4,000 to 6,000 amps on a 40 amp circuit breaker? How fast, I never mentioned this, how fast does electricity travel?
Second.
Yeah, essentially it's the speed of light, which is 186,000 miles per second. So we have electrons traveling the speed of light over a distance of, who knows, maybe a few hundred feet. That's pretty quick. How fast does a circuit breaker trip?
probably slower than that.
let's see,
Yeah, circuit breakers don't travel the speed of light yet. I don't know if they ever will, but they travel. They trip pretty much instantaneously. They trip fast, but they don't trip as fast as the speed of light or as fast as electrons. So the electrons are pushing those amps through the conductors, burning up my wire strippers, and going back to the source. But I put 4,000 to 6,000 amps on this circuit breaker. So this circuit breaker needs to be rated for that amount of inrush current. It's called AIC.
It is almost 100 times, right? And
That's what,
I'm sorry?
100 times almost. It's 40 ampere, 4,000 amperes.
Well, this could have been a 20 amp circuit breaker and it could have been the same. I was just describing the amount of damage that it did to the steel tool. I read a study that showed that was approximately what it would be. So what it was, don't take that and multiply it and say that it's about that, because there's too many factors involved. So, but to do that amount of damage on a steel tool, you're talking about 4,000 to 6,000.
Wow.
And again, that's the surface area, because it was such a small surface area. So had it been a large surface area, it wouldn't have done any damage at all. It just would have accommodated that ampacity.
That happened to me when I was doing lighting, overhead lighting,
Uh-huh.
and I'm not sure exactly what happened, but I had cutters, diagonal cutters, and it made a little circle in part of the one of the sides of the cutter there, but I don't think it was 4,000 to 6,000 amps. Is that
Why
right? Huh? Oh, because this is it was just 277.
Okay. This could be 120 volts. Although it's a factor, it doesn't exclude the chance that to burn and melt steel on a small surface area, it takes thousands of amps. Maybe it wasn't 4,000 to 6,000, maybe it was 2,000.
Oh, okay.
So I don't know about your particular situation. So what happens is at AIC, we have amps interrupting capacity. So all fuses have an AIC of, so this is for fuses, 10,000 or more. So all fuses have a 10,000 AIC or more. So all fuses are manufactured to accommodate 10,000 amps of inrush capacity or more than that. Now that doesn't mean that my 5 amp fuse won't burn at 10,000 amps. It just means that at 10,000 amps through that for a short amount of time, it's not going to explode. It's not going to obliterate. So it's not going to do what maybe my tool did. Now for circuit breakers, it starts at 5,000 or more. But generally, it's 10,000. I would be surprised to find that someone could buy a circuit breaker that's 5,000 AIC. The industry minimum now pretty much is 10,000. All your panels in your homes, if you have a panel within the last 10, 20 years, are probably 10,000 AIC. Any circuit breaker you buy at Home Depot or Lowe's, it's going to be 10,000 AIC or more.
That's not like fuses like that. You're not talking about automotive type stuff. You're talking about something for structures. Maybe.
I'm talking about what's made for the electrical industry. So specific to automobiles, I can't say, but for commercial or residential electricians, this is our book that tells us what we're allowed to do and how things are supposed to be made. And this book says 10,000. So anything that you should be using here in your career is going to be 10,000. If they have automobile fuses that are different than that, I don't know. I don't have the expertise to answer that. So amps interrupting capacity. This is the available fault current also. So if I have at your facility, you don't have 10,000 AIC breakers, it's probably well above that. I would be surprised if you're not 65 or 100,000 amps interrupting capacity. So what does that mean? It means when you cut this wire, you could potentially have a bigger problem than just, oh, I damaged my wire strippers. Maybe you melted the tip off. Maybe you burned your hand. Maybe you put an arc flash in your face. Maybe the panel explodes. I don't know what's going to happen. But because you have high voltage panels and then a very short distance, you have your low voltage panels, that becomes a factor. What also becomes a factor is the size of your system. So if you have, here are some things that are to consider. Distance. So the distance from your service or your transformers are from your high voltage side to low voltage side, the distance from there to where the arc flash occurs will depend on how much current flow is going to pass through. So if I'm at a circuit breaker and I have a 40 amp circuit breaker and my breaker's tripped and someone said, hey, the lighting's off, and I go over there and I see the circuit breaker's tripped and I turn it back on, 1, 2, 3, 4, 5. 5 seconds, the circuit breaker trips again. That's telling me that I have a fault of some sort, but my problem is probably farther away than being close to the panel, which is kind of good for troubleshooting. We know that, well, it's likely, not always true, but likely I have a problem far away, and now I can start, if I'm going to be splitting a circuit, I'm going to split the circuit down a ways as opposed to, right, I'm not going to start troubleshooting right next to the panel. It has other benefits too, but again, that's going to, because it's farther away, it's going to reduce the amount of fault current. Also, the sensitivity of the breakers. So some breakers are instantaneous trip or faster tripping. So we'll call that trip time. So if a circuit breaker or fuse can trip extremely faster, the faster it trips, it reduces the available fault current. So, and sometimes that's a bad thing. Sometimes it's a bad thing, because let's say I'm here working on this receptacle, and I accidentally touch the hot wire to the box, and instead of tripping the circuit breaker to that receptacle, I trip the main breaker at a panel somewhere. I don't want to turn off power to the building. If it trips, I want to just trip the circuit breaker to that circuit. But sometimes some breakers and fuses will trip faster than the ones down the line. I might have 2 or 3 breakers later, I might have protection for the circuit breaker, but because the trip time is so much faster for that main breaker, I'm turning off the whole building, and we don't want it. We don't want that. We want to be able to open the circuit quickly, but we don't want to also be damaged, or we also don't want to cause nuisance tripping on circuits that aren't applicable. So we got distance for the fault. We have the trip time that reduces the fault current. We also have the available fault current. Available fault current. So the utility company has transformers, and how far their transmission line, how big their transformer is. Is it a transformer a 150 kVA? Is it a 15 kVA? I mean, how big is the transformer that they have? How big is the transformer that you guys have? If it's smaller, the smaller it is, and the smaller your available fault current is going to be, because it's only going to be able to allow so much fault current to pass through that transformer. So those are 3 things. There's probably a bit more than that, but these are the 3 big ones.
What is the meaning of AFC?
Available fault current.
Available fault current.
What's available fault current from the utility?
Okay. And AIC means
The
ampere.
amps interrupting capacity. So if the breaker has the capacity to withstand 100 amps or 1,000 amps, 10,000 amps, excuse me, then that's what it's capable of doing. This is what happens. This is how it gets screwy. You have a panel in the next room here. It's a 100,000 amp AIC looking panel. It's a very expensive panel. It's got more heavier duty breakers. They're thicker. They're more expensive. That panel fails for one reason or another. It's got some bad busts. So you remove the panel. You start looking online for a new one, or maybe you have a new one in the shop. You're like, hey, here's another panel. Let's stick this thing in here. You put that panel in here. Well, is it the same voltage? Some panels are 600 volts. Some panels are 250 volts. Some panels are 100,000 amps interrupting capacity. They're rated for that. Some are 10,000. You put a 10,000 AIC rated panel where 100,000 amp rated panel was, then let's say you have a fault condition. Once you have a fault condition, someone goes over there, well, I have a tripped circuit breaker. You go to flip it back. Well, now you're making contact on that fault right in front of you. So that arc, instead of being down the line, it's right in your face. So you might have 80,000 amps traveling through that circuit breaker that's only capable of 10,000 amps. That could explode. So that's not safe. You need to make sure that you put the right AIC back. You need to also make sure that the right voltage is being put back. If you have a 600 volt panel or a 600 volt fuse or circuit breaker, it needs to be replaced with a 600 volt. when I was at another tunnel, they have a different problem than you guys have. They have a facility that's about 70 years old. And over time, electricians and people were making changes, fixing things, installing pieces of equipment, removing pieces of equipment, repairing damage. And let's say we re-pull all these conductors and we had 10 conductors in a wire. Well, you know what, I don't need that one, I don't need this one. And all I have is black, so we're just gonna pull 12 black wires through this raceway. Now I got 12 black wires, I don't know which one's which. Nobody does, they're not labeled, they're all black. And some are spare, some are not spare, some went away. Now maybe I used the wrong size wire, maybe I used bigger wire, so now it's less conduit. I don't have as much fill, or I don't have as much room in the conduit. I don't have, or maybe I'm using additional wires. So before I had 4 current carrying conductors in the raceway, but now I have 16 current carrying conductors in the raceway. When one conductor gets hot and another, they feed off of each other and they build the ambient temperature in the raceway until possibly the temperature erodes the value of the insulation and damages the insulation. So we have to be real careful about making changes, or when we do repairs, we want to repair things as close to possible as the way they were installed originally. Because after 70 years there, it's kind of a nightmare. When you come here and you see a brand new facility, you see brand new electronics, like raceways, new conductors. Although you're really close to the coast and you're going to have damage from the coastal conditions, everything's new. So when things do fail, replace it the way it was originally, please. Because eventually, you're going to have changes over time. You're just going to veer off course.
Yes.
So whether change a panel, breaker, make sure everything's the same as what it was there.
But, you talking about over color cutter?
I didn't want to throw them under the bus.
Oh, yeah. Don't
Especially if
worry.
it's just a video, but yes, the color side.
Yeah, because I remember we worked in the Posey building, we were down in the lower for replacing lights, and yeah, they was doing something. I was like, I don't think that was a good idea to use.
Yeah, they're trying to keep their facility going.
Right.
I commend them for that, but over time, I mean, 70 years,
Yeah.
that's a long time for
Yeah.
changes to take place. I mean, you're not, and then how many different people were working on stuff in those 70 years? I mean,
Yeah.
if I work on something and then 5 years later, Sean works on it, and then 5 years later, and then 5 years later, and 5 years later, 5 years later. I mean, by the time he's working on it, he's like, what the heck happened here? Who are these yahoos? And he doesn't know that 5 other people worked on it previous to him. So we want to install things and repair it to the, as best as we can to the original way it was installed. Let's see, circuit breakers. Let's talk about a troubleshooting issue that the circuit breaker trip time will help us to determine. So, let's see, so I have blue, and I have black, a circuit breaker, and let's say the circuit breaker is 30 amps. This way. And go. Alright, so we have a lighting circuit. Alright, each one of these, you guys aren't getting tired, are you? You guys ate too much?
Yep.
Does anyone go fishing on their lunch break? Because I know I would. I mean, it's only 30 minutes, but maybe I would take an hour long lunch. But you probably can't because you have to be here, huh?
Yeah.
Yeah, no problem.
All right, so we have 9 lights. Each one of these are light fixtures. I know there's back drawing you can see here on the. It's kind of making it more hard to see. I probably should have cleaned this up a little bit better. So I have 9 lights. Each one of these is drawing 1 amp. I have a 30 amp circuit breaker. How many amps do I have?
9.
9. I have 9 lights. They're all carrying 1 amp. They all have, they're 240 volt. So I have 2 hot wires going out. I got the red wire and I got the blue wire. The red wire touches each one, and I got the blue wire which touches each one. 1 amp goes to here, to this light, jumps over to this blue wire, and then comes back here. And that happens to each of these lights. So we get a call out. We're all gonna show up. All the lights are dark for some reason. Something happened. I'm gonna draw to you what happened, but let's find out how we can determine if what happened. So the circuit breaker trips. The power's off. As I said, we turn it back on. The circuit breaker takes 5 seconds for it to trip again. 1, 2, 3, 4, 5. It trips again. So, what are some techniques we can use to determine maybe where the problem is?
We check the 3 circuits one by one.
Check the 3 circuits,
One by one.
one by one. That's an option. It's not my first choice, but it's certainly an option. What are some other ideas? The hint is it takes 5 seconds for it to trip.
It will
Check the
flash.
furthest, take the furthest, load from the
Furthest
breaker.
Well, that's possible. That's an idea. But I can see here I have 1 leg, 2 leg, 3 legs. It splits off. So this one's the furthest, this one's the furthest, and this one's the furthest. So I got 3 different options of what might be the furthest. But that's possible. What else can I do? Let's use Ohm's law and what we know about testers and what we know about the 5 seconds.
The furthest point, the furthest distance, or?
See, that's where Huey's getting at. So if it takes 5 seconds and I turn the breaker off and I turn the breaker back on and I have my tester on amps and I'm there at the panel, what am I going to see here?
You should see a.
I'm gonna see 9. And then the circuit breaker is going to trip after 5 seconds. I'm going to turn the circuit breaker off. I'm going to turn the circuit breaker back on. What am I going to see? I'm not going to see 9 this time, because remember, we're grounded. It's going to be in excess of 9. It's tripping the 30 amp breaker. I don't know how much it's going to be, but it's going to be over 30 amps. So if I'm checking this one, it takes 5 seconds for the breaker to trip. I see 30 amps on this. I know I have a problem on this wire, and I know that this wire is fine. So we've just determined that without becoming exposed to live conductors, we're using an amp probe. I know that this wire is bad, this wire is good. This one has 9, this has more than 30. I also know that this one is grounded, because if this one had a problem with this one, I'd have overcurrent on both of them. And I only have overcurrent on this one here. So I know that this one's bad, this one's going to ground, this one's fine. So I already know what conductor to look at. Were you guys just sitting in?
Yeah, we're just gonna fire and
Hopefully it looks viewable. I mean, this thing doesn't erase very well.
They bought the same board I have.
All right, so we know we have a problem here. We have over 30 amps. It's tripping the breaker on this conductor, which ends up being our blue wire. But it keeps tripping. We don't want it to trip. We want to be able to troubleshoot this without the breaker tripping, so we can find out where the problem is. what happens if we disconnect the wire from the circuit breaker and put a wire nut on this? If we take this off the circuit breaker, let me put a blue wire nut on it. So we can see that's the blue wire. I put a blue wire nut on it. I check ampacity on this. What am I going to see? And I reset the breaker.
There will be no current.
Huh?
There will be no current.
There'll be nothing.
Yeah, that will be not.
Is there a path back to the source?
Yeah, it's the ground.
So how many amps would be on here?
9.
Probably about 9. Now we've changed the voltage, so it might be different. But let's just roll with the 9. We have still 1 amp on each fixture because again, when we change voltage, our ampacity can change because our wattage has changed. Our resistance is still the same, but we have. Let's say we have 9. We're gonna have something. It's gonna be close to 9. It might have changed a little bit, but let's say we have 9 amps on this wire. Is that going to trip the breaker? How many amps do we have here?
More than
0.
Oh, 0 right there. Okay,
Because we took it off the breaker,
right.
put a wire nut on it.
That's
How
it.
many amps do we have here on the ground? Going to ground.
Should be. Is it 9?
We have 9. So
So the circuit will be complete through ground, it means?
the circuit is complete because it went through the ground and it traveled back to the source because the source is grounded. So we have ground in the field, we have a path back to the source. This is grounded. Now I personally never do this and leave it overnight. But if I'm working on a circuit, I will do this. I'll let people know if there's people around. If I'm on the highway, I'll just do this during the day. At the end of my shift, I'll turn the circuit breaker off because I have voltage going through the ground, going through something.
Oh,
I don't
nice.
want a pedestrian leaning up against a light pole or something that now they have current traveling through him because it's coming back to the source. It's going through the earth back to the transformer. I can't control it. I want to keep it on a wire. I don't want it to travel through the ground. So this would not trip the circuit breaker. It's traveling back through the ground. I have no amps here, but I have 9 amps here. So let me show you 9 amps. So how does this help us with troubleshooting? We've identified what wire it is. We've identified what the problem is. We have a ground fault. We just don't know where it is. We have 9 amps here. So we know we're going to have 9 amps here. We're looking for 9 amps with our amp probe. Every time we open up a box or a light fixture or anything that we have access to wires, we don't need to put on our arc flash face shield. We don't need to put on our rubber gloves or our arc flash clothing because we're just looking for amps. I don't have to dip my probes out and test things. I'm just going to go and look for amps. So I come up to here. How many amps am I going to see? I just hold it here until I get the number I want to hear. No, it's not 9. I got 1, 2, 3. Remember, it splits off here. So I have 3 amps right here. I have 3 amps on this one. Well, if I have 3 amps there, how many amps am I going to have here?
3.
Because there's an amp jumping from there to there, an amp jumping from here to here, an amp jumping from here to here in this fixture. So here I have 3. What about right here? I lost 1 amp.
1.
I lost 2.
1.
Now I only have 1. I only have 1 amp going through this fixture back on here. So whether I'm here or here, this is 1 amp. This would be 2. See that? But what about down here? You don't see it? All right. So this light uses 1 amp. It will allow 1 amp to pass through it. So it takes an amp from here and passes it to here. If it allowed 2 amps, then this would be 2 amps from here. This would be 2 amps to there, and this would change from 9 to 10. So this light will only allow 1 amp to go through it because that's what it's using. So it's taking 1 amp from here, put it to there. If it'll use 10 amps, it'll put 10 from there to 10 to here. So there's only amps on this red wire because this light allows it.
Asking for it.
Yeah, essentially you can use either term. But if this, so whatever this is gonna allow or ask for amps from this wire, or to use, it's gonna take it from the one that's working to the one that's not working. So the red wire is the one that's going from a breaker, and this one that's not working, but it has a path back to the source, it'll put it on there. So it's, at each location, it puts an amp on it. So here would be,
3 amps.
is that true?
Yes.
It is true. And that would mean
2.
2
One.
and 1. Okay, now this is the kind of tricky part here. So we still have 9 amps here. We're gonna have 3 amps here, 3 amps here, 3 amps here, 3 amps here. How many amps here?
1,
3.
3 still. We're
rated.
still gonna have 3 right here. And let's see.
Oh,
How many we're gonna have right here?
nothing?
1.
I'll hold it.
Still not 1?
It's still not.
It's 3?
None.
Zero.
I said.
How many do we have here on this blue wire?
3.
How many do we have here?
3.
Now how many do we have here?
3.
That one, not, no.
I have 3 here.
Oh, no, you don't
Plus
have.
3
One.
here is
One.
equal to
6.
6.
Okay.
So now look,
Oh.
like I said, the red wire, the lights are taking 1 wire on the red, or 1 amp on the red and putting it on the
Oh,
blue.
okay,
So I
okay.
got 3 amps coming back this way, going back to the source. So they've got 3 amps here, they got 3 amps here. So right here, I have 6.
Yes.
So I have 6 amps here. Does that make sense? I got 3 here, I have 6 amps here. All right, what about right here?